Okay, so this is a long wire carrying a current of 6 amps in that direction, and it bends inside that magnetic field. We know the magnetic field, and we need to find the magnitude and the direction of the net force that the magnetic field exerts on the wire. So we can do this piece by piece. So if we go on the first piece here, and you can see, we know that F is equal to I dl cross E. Um, Now, if you do the right-hand rule on this, of course, we are only concerned with the piece that's inside the magnetic field, because inside the circular magnetic field, outside there is no force. So on that piece, if you is at the same time, if you consider the bottom piece, which is let's call it 3 here, or 2, you can see that the magnetic field is still the same, but the current reverses direction, so the magnetic force will be as such. And those two forces will, on each and every single piece, we have one like this and one like this, and so the net force of net from pieces 1 and 2 will just be 0. They'll cancel each other. Piece, the current is going down. So if you do the right-hand rule, so current DL is down in the negative Y. If I take my Y to be downwards, upwards positive, downwards negative. So down and then out of the page, and then the force will be to the left. So this is my F on segment number 3. So if I were to find my F3, that's just I. And then if I call my DL, so if this is my X and this is my Y, DL would just be minus dy crossed with, so if I call my Z to be out of the page, so this is times the magnetic field B in the Z direction. So this is in the K, and the dy is obviously in the negative J. And if you take the cross product of these two vectors, this will give me a small infinitesimal piece of the force if I were to take a small piece. And then, of course, if I integrate this 0, where the piece starts, to the length of the piece is 0.45 meters, because it's 45 centimeters, I would get the entire force on the entire segment. Now, of course, I is uniform, so I could have pulled it outside the integral. The cross product between J and K, like we said, is minus I. So then I will get minus I times B. The magnitude is uniform. I can take it out. And this is just dy. And this is again is I. And then I'm integrating y from 0 to 0.45. So I would get minus I, which is, so then if I integrate this, I would get F will equal to minus, the current is 6 and B is 0. 0.666 Teslas. The integral of dy is just y, so this is minus IBY from 0 to 0.45, and of course the answer is just times 0.45 in the I. So this is the magnitude of the force. This is the vector form of the force, and if I were to take the direction of this, the magnitude of this force, the answer will be 1.80 newtons, pointing to the left of the arrow. Now, just as a note here, the shape of this magnetic region by no way alters our result, as long as the length of the piece of the wire inside the magnetic field is the same in both cases in which we are assuming they are, because it's symmetric. Otherwise, of course, the entire force will not cancel out. This does it for this question. Please don't forget to like and subscribe. I really need your subscription to keep this channel going. And thanks for watching.